because Arman is obliged to give us this information. So this is one requirement from the fellowship. So we will all know more about our national center.
Yeah, quite more than okay. So thank you very much for giving me the opportunity to talk here. So as Jacek said, this is a rather special talk since I have to include a lot of non-mathematical material. So I must promote the fellowship, which is quite fair in a sense, since without them I wouldn't be here. So, okay, so this is the structure of my course. So it's roughly split into three parts. The first part is about the Paul's Fellowship. The second part, from the second part on, I will delve into mathematical ideas. I would say the second part is more historical. There won't be anything new. And the last part is on the latest development in the field. Okay, so let me start with the fellowship itself. So the fellowship is funded by Norway grants, which is a financial mechanism funded exclusively by Norway for the period 2014 and 2021. And it aims to promote cooperation and strengthen ties between Norway and the European Union. And also, it aims at reducing the disparity in research performance across Europe. So there were quite a few European countries benefiting from these grants, mostly from Central Europe, and Poland was actually its largest beneficiary. In Poland, there are, I think, two programs, and one of them is the basic research program that focuses on pure research, and it covers science, technology, and the humanities. And it is operated by the National Science Center, the NCN, and in collaboration or in coordination with the Research Council of Norway. So it aims to boost the research potential of Polish research institutions, such as the University of Warsaw, to increase scientific excellence and to support researchers, such as me, consolidating their research careers. Okay, so the Poles Fellowship was one of three fellowships available. So there were three calls, and this was the last one. And it's a smaller grant, which focuses on researchers based abroad and encouraging them to move to Poland and contribute to science and humanities in Poland. And it was awarded on the basis of its scientific excellence, relevance, quality of implementation, and potential impact of the proposal. So my proposal focused on mathematical methods in general relativity. So more specifically, we shall investigate the conformal and complex properties of space-times in dimensions 4 and higher, with a focus on congruences of null geodesics. So I'll explain what this means later. And in particular, we shall examine the interaction between Lorentzian geometry and almost CR geometry, which is not very well known, but as it happens, Warsaw was really leading the field in the 1980s and 1990s. So this is one part of the proposal, and the other part is a little bit different. And the idea is to apply conformal methods, modern conformal methods, to the study of horizons and related geometries. So this could include black hole geometries, for instance. So the outcome, well, hopefully, I think we're pretty certain that this proposal will lead to a deeper conceptual understanding of geometries arising in general relativity. And also, it should lead to new solutions to Einstein field equations and horizon geometries that are really relevant in general relativity these days. Okay, so so this is the team, if you like, of the research of the fellowship. So the basic team is at the Faculty of Physics here. So I'll be the principal investigator, and I'll have 3 co-investigators. So the main one is Professor Jerzy Lewandowski, and we also have 2 doctoral students. So this is, initially we had planned only 1, but we decided to go for 2, 1 for each part of the project. And since it's a Norwegian grant, we might as well involve people from Norway. So we have some international collaboration going on. So we'll be working with Boris Kruglikov and Dennis Fe at the Arctic University of Norway in Tromsø. So this is the northernmost university in the world, just above, well, just north of the Arctic Circle. And these people are interested in carton geometries, CR geometries, invariance and symmetry. So actually they've done pretty good work on CR geometry recently, especially in higher dimensions, 5 dimensions. And their work should be very relevant to this fellowship. And then we have Rob Gover, based at the University of Auckland in New Zealand, and he's a collaborator of mine. I've already collaborated with him, and he's an expert in tractor calculus, which is a conformal invariant calculus, carton geometries, and applications to physics. So of course, this is not an exclusive list. So this is what we had for the proposal, but anyone from this faculty who is interested in this topic is welcome to contribute. And also we can reach out to other institutions in Warsaw, such as CFT PAN, IMPAN, and also institutions in Poland and beyond. Okay, so this is the structure of my fellowship. I mean, this is I've already talked about it. So it's divided into 2 parts. The first part on the interaction between Lorentzian geometry and CR geometry, and the second part on horizon geometries from a conformal perspective. And so each part will take roughly 1 year. So horizon geometries is a hot topic, at least here. This is led by Professor Lewandowski, and so it's in red color. So we're moving from something that is a bit frozen, which is not so popular these days, so this interaction with CR geometry, and moving to a more popular subject. So the division between the 2 parts is not really clear-cut, and we have events associated to this fellowship. So we'll have the opening lecture, which is right now, and the closing event. And in between, we will be organizing 2 workshops, one midway through the fellowship and the other one near the end. And next term, I will be giving a lecture course on topics related to the fellowship. So it will be on conformal and CR methods. So on the agenda, we'll have research trips as usual, and also we'll have a dedicated website. For these workshops will be in Warsaw? Or? Yeah, in Warsaw. Yeah. So it still needs to be organized, but I think next semester it should be fine. So it will be mostly for graduate students, but it might be quite advanced. So I guess faculty members are also welcome to join. Okay, so let me carry on. So I'm usually very modest about myself. I don't like talking about myself, but I have to introduce myself. So I graduated from Glasgow University in 2005, and then I went on to do my PhD at Oxford under the supervision of Lionel Mason. So I owe Lionel a lot, since he's the one who launched me into this area. And he made me work on spinors and twistors as applied to general relativity, but in higher dimensions. So these methods were very, very popular. Well, they're still very popular in 4 dimensions, and they were promoted in great part by Roger Penrose. And so I started with this kind of field. Then I spent a year teaching, and then I had I spent a lot of time in Jan Slovak's group as a postdoc at Maastricht University, where I managed to secure 2 grants. One being a Marie Curie fellowship, Marie Skłodowska-Curie fellowship, and another one a Czech Foundation fellowship. And I thought my research interest changed a little bit. I became more interested in pure differential geometry, and it opened me a lot of doors to different directions in the field. So until then, I had worked mostly on spinors and twisters and conformal geometry, but then I became acquainted with projective geometry and a little bit more CR geometry and tractorial methods. So I haven't explained what tractors are, but and I won't in this talk. But if you like, the tractor calculus is an invariant type of calculus. It's you can think of it as the conformal analog of the Ricci calculus for Riemann geometry. Anyway, so then I spent a year in Turin with Anna Fino, and I returned to a topic that actually was born here in Warsaw with the work of Paweł Mrowski and Andrzej Trautmann. So this is called almost Robinson structures. And I had been thinking about it for a long time, but it seems that after I had spent many years working on different geometries, I managed to find methods to solve the issues related to this project. Okay, and then I moved to Beirut, where I was an assistant professor, and it was a very messy period. So this period here does not really reflect my time. So I was in Beirut only physically for 2 years, and then I was on leave because of a number of problems there. So there is no mention of Poland, but actually I had been to Poland a few times already. So I already have a connection to Poland. So my first trip was actually to Krakow for a conference then. Then I think it was in 2013, I came here for this GR20 conference, and I visited Paweł Mrowski, with whom I was collaborating then. And I made various visits to CFT PAN and InPAN. I spent 2 months in Warsaw as part of a semester fellowship. And my first visit to this faculty was in January 2019. So here I should really credit Adam Sieryszewski, because I was giving a talk at InPAN, and Adam Sieryszewski was actually spying at InPAN, and he thought I could give the same talk at this faculty, and so he invited me to join and give a talk here. So this is how I met people here. I think I had met Jurek already in 2017 in Cerny, a conference in a winter school in the Czech Republic, and Jurek was giving a course on horizon geometries then. Okay, so this, after several applications, I eventually managed to secure this Pols fellowship at this faculty. I have no idea. Actually, most of these fellowships have names after musical terms, but this one does not. Yeah, I don't know why. Okay. Okay, so let's do some maths. So I have spent quite a lot of time on this. Okay, so I will focus on only one half of the fellowship. So the first half, the one that is connected to CR geometry. So I will give a historical review of the development that happened during the Golden Age of Relativity. So that is in the late 1950s and early 1960s. And these developments led to this interaction between Lorentzian geometry and CR geometry. So the central point, the central notion here is that of a non-shearing congruence of null geodesics on a 4-dimensional Lorentzian manifold. So I will refer this to as space-time. And you can think of this as being the set of integrable curves of a non-vanishing null vector field. I'm sure you're all familiar with the notion of the null vector field. So GKK is equal to 0, it has 0 length, and it satisfies this property. So this is the defining property of non-shearing. And this means that the conformal class of the metric G, when restricted to the directions orthogonal to this vector K, is preserved along the flow of K. So this is what it means. So there are 2 basic properties. One is that this equation is conformally invariant. It doesn't really matter if I change the scaling of the metric. And similarly, if I change the scaling of K, then this is also invariant. Of course, alpha and epsilon will change, but the basic formula remains the same. So I can actually study these objects on a conformal structure. And instead of looking at the vector field, I can consider the null distribution spanned by this vector field. Okay, so let me give you an example. So this is actually the example of the simplest possible congruence of, non-shearing congruence of null geodesics. So this is due to Robinson, but the example is drawn from this article by Nurowski and Trautmann. So I can cast the Minkowski metric in these coordinates, so I've got U and B, real coordinates, and then I have a complex coordinate Z. So you can think of Z as being X plus IY. And I have this vector field K, and I can check that it is a geodesic, and V in this case can be thought of as an affine parameter along the geodesics. And if you compute this equation, you see that the congruence of null geodesics is actually non-shearing. And the other property is that the congruence is twisting. So if I take kappa, kappa being given by the one form associated to K, then kappa wedge d kappa is nowhere 0. Okay, so what is that good for? So you want to have an application for such congruences. So going back to this example, so let's consider this complex 2-formed phi. So take kappa, which was the one form associated to the null congruence, and wedge it with dz, and then you can check that phi is a closed, totally null self-dual complex 2-form. So it satisfies all these properties. So we want to get back to the real world. So we take phi and we add to it its complex conjugate, and you get a real null 2-form F, and we discover that it satisfies the vacuum Maxwell equations. So it is a closed and co-closed 2-form. And this equation is also conformally invariant. So here conformally invariant is particularly important. Now we have this, we can generalize this, this example to an arbitrary non-shearing congruence of null geodesics. So this is known as the Robinson theorem. So locally, any analytic, so here I'm emphasizing analytic because there are issues related to analysis that crop up. And indeed here, since we have used complex variables, there is an analyticity issue. Okay, so locally, any analytic non-shearing congruence of null geodesics gives rise to a null solution to the vacuum Maxwell equations. And there is also a converse. So if you start with a solution to the vacuum Maxwell equations that is null, then you can find a non-shearing congruence of null geodesics. And actually, the converse was found a lot earlier. There is no need to assume analyticity, and it's much easier to prove. So I won't give you a proof now. I don't know if I'll have time to give you a proof. Before this, in any case, I want to tell you about the obstructions to the existence of such congruences. And this is given by the Weil tensor, which is the conformally invariant part of the Riemann tensor. So not every space-time can admit such congruences. But the integrability condition is particularly weak. So if we have a non-shearing congruence, then K must be a principal null direction of the Weyl tensor. So if you don't know what this means, this is what it means as an equation. So it's actually a very weak condition. And in fact, at every point, you can always find a null vector field that satisfies this property. So it's not very interesting, but there is a very important theorem of general relativity, which is known as the Goldbach-Sachs theorem, which tells you that if you restrict yourself to Einstein spacetimes, then K generates a non-shearing congruence of null geodesics, if and only if it is a repeated principal null direction of the Weyl tensor. So this is a slightly stronger condition on the Weyl tensor. So according to the Petrov type classification, we say that the Weyl tensor is algebraically special. So there is this Einstein condition, which is not quite conformally invariant, but there are conformally invariant versions of this theorem in other literature. Okay, so this theorem is particularly important because many important Einstein metrics are algebraically special. So here are a few: the Schwarz metric, the Robinson-Trautmann metric, Kerr-Taub-Knot, and so on. And well, so for instance, let me tell you about the Kerr metric. So that was discovered in 1963. So it's a Petrov type D Einstein metric describing a rotating black hole, and it admits actually two non-shearing congruences. So this comes from the fact that it is a type D metric. And one property of this metric is that it can be cast into this form. So you can think of it as an exact first order perturbation of the Minkowski metric. So here kappa would be some null vector, and we know that it is non-shearing congruent. It generates a non-shearing congruence. And an important fact is that if K is the congruence generated by K is geodesic and shear-free or non-shearing for eta, for the Minkowski metric, then it is also for G. So if you want to find non-shearing congruences in Minkowski, in some spacetime, admitting a Kerr-Schell metric, then you can try to find such non-shearing congruences in Minkowski space. And the solution for this is given by another famous theorem, which is known as the Kepler Theorem. And it tells you that any analytic non-shearing congruence of null geodesics in Minkowski space can be locally obtained from an analytic function of three complex variables. So this is this statement is very vague, and I've kept it vague deliberately, and still a bit mysterious. And I will show you the appropriate geometric interpretation of this theorem later. Okay, so we've been mentioning this complex stuff. So you know, when you work in Lorentzian geometry in general relativity, unless you want to make contact with a quantum theory, you might think that there is no need for complex numbers. But actually, as my previous slides have shown, that the complex numbers show up in a number of places, although you seem to be starting from something that is real. So why is this? So the key point here is that if you start with a null distribution, so a null distribution spanned by a distribution spanned by a null vector K, then you can find a null coframe, kappa, mu, bar, lambda, such that the metric is in this form. So kappa here, again, is the one form associated to K. And so this null coframe is not defined uniquely. So any other adapted coframe to this null distribution must be related to the first one by these transformations. And here you see that this kappa is only rescaled, but here this mu, which is a complex one form, becomes another complex one form plus the addition of this kappa here. So what this means is that you can associate to a null distribution K, a complex distribution. So which is annihilated by these two forms, kappa and mu. So this would be an invariant of the geometry. So, okay, so here there are some conventions to follow, but we'll brush this under the carpet. So we define an alpha plane distribution to be the distribution annihilated by kappa and mu. And if you take the complex conjugates, you get another distribution, which is called a beta plane distribution. And the alpha plane distribution is self-dual, and the other one is anti-self-dual, and they complex conjugate to each other. The complex and totally null. And the key facts, so I mean, you can start with a complex distribution that is totally null, and you can recover a null line distribution. So the key fact is that null line distribution are equivalent to alpha plane distributions, or equivalently beta plane distributions. Okay, so initially I had a slide on spinors, but it became a bit too complicated. So this actually summarizes the essence of spinors in dimension 4. So this interpretation, basically, I mean, it seems to be really trivial because people in GR use it all the time, but it really comes from the spinorial approach to GR, to the general relativity that was advocated by Lewis Witten, Roger Penrose, and so on. And it tells you that an alpha plane distribution or a null line distribution it can essentially be encoded in terms of a spinor field up to scale. Okay, so another key fact. So now that we have a relation between the null line distribution and the complex two-plane distribution, alpha plane distribution, we want to see how the different differential properties are related to each other. So there is this key fact that tells you that K generates a non-shearing congruence of null geodesics if and only if its associated alpha plane distribution is involutive. So it means that you take the D brackets of any two sections of the alpha plane distribution, then it lands in the alpha plane distribution. So here there is an issue. I've used the word involutivity, not as a synonym of integrability. So here okay, so I'll go quickly. Involutivity is not equivalent to integrability in general, in this particular case, because you're mixing real variables and complex variables. So I will not go into details. So the one solution is to assume that all our quantities are analytic. And if you do that, you can extend your original manifolds to a complex Riemannian manifold. So then this is a holomorphic manifold. This is a complex manifold equipped with a holomorphic metric. And you can think of your original real analytic manifold as being a slice, a real slice of your complex manifold. If you do this, then by the Frobenius theorem, an integrable alpha plane distribution gives rise to a foliation by alpha planes, the alpha surfaces, sorry, in the complexification of this manifold. Okay, so I wanted to draw something, but where are the chalks? So maybe the picture to have in mind here oops. So, okay, so yeah, so maybe I'll carry on a little bit. Okay, so what you have, okay, so you have beta planes. So you have alpha surfaces coming from one foliation, and you have beta surfaces coming from another foliation. So think of it. So first of all, the first picture to have in mind is that so the complexification. So you can think of M as being a real slice of a slightly thickened manifold, which is its complexification. I mean, think of the complex plane as being the complexification of the real line. And if you do this, then your alpha plane distribution will give you a foliation by alpha surfaces. So you'll get an alpha surfaces here. And then you have the complex conjugate of the other one, I mean, which are the beta surfaces, and they will intersect the alpha surface the alpha surfaces in a complex null line. So this will be a complex null curve. Sorry, complex null curve. Okay, so this is a beta surface here. And so this intersection is a complex null curve. And it happens that it is actually complex null geodesic. And if you restrict yourself to the real slice n, you'll see that what these foliations are doing is that they're generating a non-shearing congruence of null geodesics. Okay, so how do I go back down? Oh, this one. See, this one is for this one. Okay. Okay, thank you. Okay, so this is the conclusion. The non-shearing congruence of null geodesics arise from the intersection of an alpha surface foliation and a beta surface foliation. Okay, so I don't think I have much time. Let me see. Oh, maybe I do. So I have 20 minutes left. Maybe. Okay, so maybe I will carry on. So then you can think of the Robinson theorem in this slide. So if you forget about the real world, so this is the trick if you want to prove these theorems very quickly. So so I remind you what the Robinson theorem is. So it tells you that any analytic non-shearing congruence of null geodesics gives rise to a null solution to the vacuum Maxwell equations. And then, okay, you have a converse, but the converse is rather trivial in a sense. So instead, I can focus on the first part. So as I've just said, you can think of your analytic non-shearing congruence as being an alpha surface foliation in the complexification of your manifolds. So you have, so you have a foliation here of the complexification of M, your complex manifold. So each of these guys are alpha surfaces. So this is full complex dimension. Each leaf has dimension, complex dimension 2. So what you can do is you can take the quotient of your complex manifolds by this foliation, and you get the leaf space of the foliation. And this is two-dimensional complex manifold. Okay, so this is the leaf space. That's what it's. So if you do this, what you can do, so you start with your foliation, your alpha surface foliation. This is a two-dimensional complex manifold. So what you take is you take a two-form, a complex holomorphic two-form. So this is a top form. So where is it? So this is a top form on a two-dimensional manifold. So you know that it's automatically closed. So then you can pull it back to your original manifolds, the original complex manifold, and if it's closed downstairs, it's closed upstairs. So this phi here is closed. It's also null and self-dual because it's transverse to the leaves of the foliation. And then, as I argued earlier on, then if you want to recover the real world, you just take the complex conjugate of this two-form here, you form a real two-form that is null, and it satisfies the Maxwell equations. So it's actually very easy to prove Robinson theorem in this fashion. Okay, so let me carry on. So okay, so this becomes a little bit more complicated. So you can play the same game with the Kerr theorem. So this is a little bit more complicated. So I start with my original version of the Kerr theorem, which tells me that any analytic non-shearing congruence of null geodesics in Minkowski space can be locally obtained from an analytic function of 3 variables. So this, again, is a very vague statement. So I can replace this statement by the complex statement, which tells me that any foliation but alpha surfaces in complexified Minkowski space. So complexified Minkowski space is simply C4. There's nothing too fancy about this, plus an inner product, a holomorphic inner product. So any foliations by alpha surfaces in complexified Minkowski space can be locally obtained from an analytic function of 3 variables, but actually one can show that these alpha surfaces are actually alpha planes. So what I mean by this is that the leaf of the foliation, or each leaf of the foliation is actually an affine subspace of Minkowski space. So this is what I call a plane, and it is totally null. So in this case, if you want to find a proof for the Kerr theorem, you can decide to consider the space of all alpha planes in Minkowski space. So there is a bit of a trick, although this is not quite necessary, but I'll explain. Okay, so you take the complexification of Minkowski space and you can view it as a dense open set, or should I say subset of a smooth projective quadric of dimension 4. And you define the twistor space of this quadric as being the space of all alpha planes, well, there in Q4. So I'm going roughly. So the point is you have to consider the space of all alpha planes in this quadric, which is the same as, roughly the same as taking all the set of all alpha planes in complexified Minkowski space. Then this twistor space is complex projective space CP3. So a projectivization of C4. But then if you have this foliation by alpha planes, then you know that the leaf space of this foliation is a complex hypersurface in projective twistors in twistor space, and therefore it must be prescribed an analytic function of 3 complex variables. Okay, so here the point is the leaf space is 2-dimensional. So each point of this leaf space corresponds to an alpha plane. So you have to have a two-dimensional complex submanifold of your twistor space as defined as the space of all alpha planes. Okay, so the picture is a little bit complicated, but this is what led. So the Kerr theorem was one of the ingredients that led Penrose to formulate his twistor theory. So if I reformulate the Kerr theorem a la Penrose, any local foliation of this smooth quadric by alpha planes gives rise to a certain complex hypersurface in twistor space. And conversely, any such foliation arises in this way. Actually, there are some technicalities that I have to leave. Okay, so the real picture, initially I wanted to give you the real picture in terms of twistor geometry, but it gets rather complicated, so I have to take a shortcut. So if you want to have a real analog, it's difficult to put it this way, but let's put it this way. If you want a real analog of this complex picture, you have to consider things called CR manifolds. So let's go back to our example of the Robinson congruence. So this is your Minkowski metric in terms of these complex coordinates or null coordinates. And we have, so we show that this null, the non-shearing congruence of null geodesics is generated by this null vector K. Then the one forms that we defined previously, so kappa is defined by this guy here, mu is simply dz and mu bar is dz bar. So these descend to the leaf space of the congruence. So why is this? Because there is no dependence on the affine parameters. That's as simple as this. So you take the Lie derivative of kappa, mu and mu bar with respect to k, this is 0. So we say that these 3 forms descend to the leaf space of the congruence. So these 3 forms descend to these 3 one forms descend to the leaf space of the congruence, and we say that the spans of kappa and mu define a non-degenerate, almost Cauchy-Riemann structure. So this is typically referred to or denoted by a pair H and J. So H is simply the distribution, the rank 2 distribution annihilated by kappa here. and J is a bundle complex structure on H, which satisfies this property. So you can think of mu and mu bar as being the 1-0 form and the 0-1 form of a complex structure. This is if you're familiar with complex geometry. Okay, so I don't have much time to deal with this, but more general fact, which is very important, well, in some areas. So this is due to a number of people, but I would say that Penrose, Robinson, Troutman, and their respective schools, either in Oxford or Warsaw, contributed to this result. So it tells you that the least space of a non-shearing congruence of null geodesics is a CR manifold of dimension 3. And conversely, to any CR3 manifolds, one can associate a space-time equipped with a non-shearing congruence of null geodesics. So I have to.
So actually, for me, the first person to notice that was Jacek.
Oh yes, it's true. I will mention Jacek later. It's true. So okay. But you can see this 3 manifold already in the CR manifold already in the paper by Penrose in 1967. But it's true that Jacek was the first to put the name CR on this manifold. So the construction initially arose in this paper.
The main point of Jacek's paper was that people used to write this Maxwell equation for this specific Maxwell field, and then they would, unknowingly, they would turn it into the CR equation, which does not necessarily have solutions.
Yeah.
Physicists would say, okay, this is a simple system of linear partial linear equation presented with solutions, blah, 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 blah.
Yeah.
Jacek pointed out that this is the famous CR equation, which is one from
the Levy problem.
Example, and that actually generically it doesn't.
Yeah, exactly. So actually, here I haven't. So I omitted the term analytic, and it's pretty much correct. I can still say this, but it's the analyticity problem comes with props up with this Robinson theorem. So this is still a true statement, but I guess Jacek pointed out this problem in connection with the Robinson theorem. You can see it actually from the proof of Robinson's theorem. So the problem comes from let's leave it. So it's when you consider the pullback of this two form upstairs to this complex manifold, then there is a choice of scaling, and this choice of scaling has to be a holomorphic function. But this might not be available if you work in the non-analytic category. Okay, so so as said here, this is what I said earlier on. You can recover this description from the Kepler theorem according to the tortuous historical narrative. So this is what we've just spoken about. So these facts were hidden in the work of Penrose, Robinson, and Troutman, but Jacek clarified a lot of it later. So actually, okay, so maybe I can start with this. So there are a lot of spin-offs. So the embeddability problem. So actually, it was already mentioned by Penrose in 1983, but not in connection with this congruence of null geodesics. With other, I think it was, I can't remember exactly. I think it might have been the non-linear graviton. But it was indeed Jacek Tattel who in 1985 started pointing out that there were issues related to the analyticity or embeddability of CR manifolds. And the topic developed further with work by Lewandowski, Nurowski, also Tattel, and later with Hill, who is a specialist in CR geometry, Lewandowski and Nurowski. So there are issues of analyticity that crop up quite often in this area. And I should also mention that so I was very much influenced by this paper by Jurek and Paweł Nurowski in 1990, which was to use these CR methods to seek Einstein metrics. So Jurek is very modest about this paper. He claims that, oh, we didn't find anything new, it was only conceptual, but yet I thought it was a very clear paper, and I used it to find new solutions to Einstein equations in high dimensions. So there was a prototype here to be used, and this was later used in this paper so the first paper is about Einstein metrics. The second one with Jacek is concerned with pure radiation, I believe. Yeah, and this embeddability problem, by the way, is connected to the existence of Einstein metrics. So I'm not going to go into details, but yeah, so this is it. Then, okay, so I'll skip this part on Pfefferman spaces. So Pfefferman spaces are, you can think of them as Lorentzian conformal structures constructed over CR manifolds. But something that really influenced my own work is this, well, the analogies between Lorentzian geometry and Riemannian geometries. As it happened, some people discovered that there were Riemannian analogs of these classical theorems of general relativity. So there is a Riemannian Dolgozar's theorem, which is due to Pshanowski and Broda, and also a Riemannian Kerr theorem. So this comes from these pure mathematicians, Gels and Salomon. And Nurowski worked a lot on this. So he really developed a theory whereby non-shearing congruence of null geodesics in Lorentzian geometry are essentially equivalent or analogous to Hermitian structures in Riemannian geometry. So he's worked a lot on this, and this influenced my own work. And then there is this stuff about twistor theory, which is quite rich. So a lot of it became, so it didn't have as much impact as it should have, well, it was expected to have in physics, but it had more impact in mathematics. So you have tools of differential geometries that were heavily developed thanks to twistor theory. So Penrose transform is one of them, tractor calculus, parabolic geometries. And it has to do more with invariant differential equations and things. Okay, so then I come to my own world, so the world of higher dimensions. So we can generalize the ideas I've just talked about to higher dimensions by introducing this notion of almost null structure. This is a very old notion, actually, but I use this terminology. I introduced this terminology, but it's not widely used. So here you can work on any pseudo-Riemannian manifold, and by pseudo-Riemannian, I also include Riemannian of dimension n, so of n signature. And we defined an almost null structure to be a field n of totally null complex n over. So this is the roof function. So this is not, I don't like this roof function, but basically if n is 2n dimensional, so 2 is equal to 2n, then n has dimension n. So dimension of n is n, and if it's n has dimension 2n plus 1, then dimension of n is m as well. So this is what it means. So they have maximal rank, you can put it this way. So for instance, what happens in Riemannian geometry, so if you take a Riemannian manifold of even dimensions, then an almost null structure is equivalent to an almost Hermitian structure. So it simply means that the complexification of the tangent bundle is simply the direct sum of n plus its complex conjugates. And so you can identify n as the eigenbundle of a complex structure J, and n bar as the other eigenbundle. So this is so this notion is intrinsically connected to the notion of pure or simple spinors, that first emerged in Cartan's work. Actually, it was in the 1930s, but there is a nice book by Cartan. The English translation was made in 1967. And then quite a few people here in Warsaw, and I guess in Trieste, worked on this. So I cannot recommend more these references. Really, they are gems in the field, because people are often scared of spinors, but these people made the subject really tractable. So especially this work by Bunig, Troutman, Kopczynski, and Troutman and Kopczynski. So it really, if you ever want to use spinors, I would recommend these references. So then some people in Oxford also worked on these pure spinors. So there is Houston, Jeffries, and myself. I worked a lot on these subjects from the point of view of G structures. So I gave a fairly detailed account of the geometry of these almost null structures. Then there is pretty nice generalization of due to Houston and Mason of the Kepler Theorem in the complex case to higher dimensions. So they worked in even dimensions, and I gave a generalization to odd dimensions a bit later. In odd dimension, the odd dimensional case is a little bit more tricky than the even dimensional case. And then I worked on generalizations of the Goldberg-Zar's theorem in the early 2010s. But there are still issues related to this theorem. Okay, so I wanted to focus on almost Robinson geometries. So this is the missing link between Lorentzian geometry and CR geometry. So these beasts were introduced by Nowrocki and Troutman in 2002, but really built on this work on almost null structures that I mentioned previously. So these are not Lorentzian analogs of Hermitian manifolds. And very recently, with my collaborators, Anna Pino and Thomas Leisner, we generalized these Robinson manifolds to almost Robinson manifolds. So what are they? So you can think of them as Lorentzian analogs of almost Hermitian manifolds. So you can think of them as a quadrupole, Mg and K, where Mg is a Lorentzian manifold of dimension 2n+2, and N is a totally null complex n+1 plane distribution. And K can be recovered from N as, so this is a real null line bundle, whose complexification is contained in N. And you call an almost Robinson manifold a nearly Robinson manifold when this distribution N is preserved along the distribution K, and a Robinson manifold when actually this distribution N is involutive. So if this first property is satisfied, it means that on the leaf space of K, what you get is a normal CR structure. So you can find plenty of examples. So actually, this is what I'm saying in this slide here. But you can find plenty of examples of nearly Robinson manifolds. So you start with an almost CR structure, which is denoted by M bar, H bar, and J. So M bar would have 2n+1 dimensions. You extend this manifold by, well, trivially, by 1 dimension. So you get an even dimensional manifold. And then you lift H and J to some structures on this extended manifold. And these structures will define, you can show that they will define a nearly Robinson manifold. Okay, I will not give all the details here. Okay, so let me give you some examples. Okay, I'll skip the Pfeffer spaces. So the point is this work really relevant to general relativity? And the answer is, well, I believe yes. So there was this first work, it was with Lionel Mason in 2010. We managed to find a discrete set of Robinson structures on higher dimensional generalizations of the Carnot ADS metrics. So these metrics were due to Chen, Liu, and Pope in 2008. but their form is, I mean, really, you can think of them as being partial generalizations of the Plebanski-Demianski metric that was discovered in 1976. So this was quite a surprise. Maybe it was not a surprise for Lionel, because people at the time were very much interested in non-shearing congruences in higher dimensions, and they couldn't find that many of them, except for Kuhn spacetimes and Robinson-Troutman spacetimes. But for these twisting congruences, typically the congruences were shearing. So it was postulated, actually it was already postulated before by Pavel Mirovsky and Andrzej Troutman, that Robinson structures would be the appropriate generalizations of non-shearing congruences to higher dimensions. And in fact, yes, for this Kerr-Nortadis metric, we find a discrete set of Robinson structures. And then I have my more recent work that got published this year. So in this case, I take a very particular situation where I consider a twisting non-shearing congruence of null geodesics in even dimensions. And under certain curvature conditions, I discover that the twist induces a nearly Robinson structure. And then I asked myself, well, so how about these Einstein metrics? Can I find any of these Einstein metrics? So this was very much related to the work of Lewandowski and Murawski of 1990. So I asked myself, can I find Einstein metrics in his, well, so it was actually a conformal structure. So in this conformal structure, and the answer is yes. And it gave me a new set of invariant differential equations that defines the notion of almost CR Einstein structures. So in this case, actually, I was looking for Lorentzian structures, particular Lorentzian structures, such as an Einstein condition, and I discovered actually invariant CR structures. And I also discovered that these metrics, I mean, there are very few of them, and they're related to the Pfefferman-Einstein metrics and the Taub-Knot AVS metrics. Okay, so this should be my last slide. So the objective of Paul's fellowship is to push this agenda of almost Robinson structures further. And one of the goals is to reduce the Einstein field equations to CR data. So this is one goal. So in dimension 4, this is recent work in progress. And this was actually an outstanding issue that, well, Jurek was interested in, Pavel Mirovsky as well, and Lionel Mason. And it seems that my recent work in high dimensions shed light on what's going on in 4 dimensions. So actually, there's been some progress, and I'm quite happy with this. So in dimension 4, as I've just said, for the business of non-shearing congruences, the work has been done, I would say, mostly done. I mean, you can drop some conditions further. And so the key point here would be to focus on Robinson geometries, which are equipped, sorry, I meant with shearing congruence. Sorry, this is a typo. Instead of non-shearing, I should have shearing. So we should focus on Robinson geometries with shearing congruences. And there are related issues concerning the Goldberg-Zar's theorems, Kerr theorems. So all these classical theorems, how do they generalize to higher dimensions? How do they relate to differential equations on CR manifolds? And we can look at global properties, and this could include examples taken from homogeneous spaces and that kind of thing. Okay, so this is only one half of the project. Maybe it's a bit too ambitious, and not treated in this talk well. So it's the conformal approach to horizon geometries. So this is for another time. So my apologies if you're disappointed with this and you were expecting some stuff on horizon geometries. But I think people here know more about the topic than I do. Okay, so I will finish here.
Somebody would like to try microphone? No. Trzeci. A mogę puścić? I have a question to this last slide.
Okay.
You say that dimension 4, you can somehow, I understand that you can write Einstein equations as conditions on Nonshearing stretch.
Yes.
What kind of conditions do you get? Very high order conditions on
Sorry, what?
higher order conditions on
No, I don't know what you mean by higher order.
higher derivatives on
the
forms defining Nonshearing.
Yeah. So okay. So it splits into two parts. Actually, you can weaken the Einstein condition. You can what you can do is you can insist on the Ricci tensor to be degenerate along the complex norm distribution on my Lorentzian manifold. And in this case, I get something that is conformal, that is CR invariant downstairs. And this is first, I would say it's, yeah, it's first order. It's is it first? Well, maybe it's actually a CR version of the Einstein-Weil equation. So actually, it's not clear if it's first order. I don't think it's first order, but it's it might be quite complicated. But the answer for the CR invariant part is that it is a CR invariant of the Einstein-Weil equations. So it's, but actually, maybe we should know, because the same equations, so you think of this near horizon equation as being higher order, or is that first order? Do you think of it as so this nabla? So it's an equation of this form. So it's not linear. It's something like this. Yeah, actually, it is higher order. So you get something like this. So something of this type. So I guess it is a higher.
No, but I asked in terms of, say, if you define Nonshearing by means of two forms, yes?
Yeah.
One real, one complex, yeah?
Yeah.
Then you can write it in terms of these forms as differentials, things like this.
Yeah. It would be only one covariant derivative in a sense. So I guess it would be first order, but it would be similar to this.
But you say that the Riemann tensor is degenerate by assumption.
No. Okay, so the Weil. So what do you mean?
No, you said that along the congruence there's some condition.
Oh no. So in 4 dimensions, actually, you don't need this additional condition. Because it follows from the Goldberg-Zaks theorem. So this is convenient in 4 dimensions. In higher dimensions, you need to impose it, although we might be able to drop it. But no, in 4 dimensions, you can reduce parts of the Einstein equations to a formula like this. So it's a CR invariant version of the Einstein-Weil equations. So I would think of it as a first order differential equation, but it's non-linear. Yeah, so this is the point. But this is not the only condition. If you want to have the full Einstein equations, then it becomes quite messy. And it's not quite CR invariance, but you would not expect CR invariance for the full Einstein equations. Because think of it this way. You have this correspondence between conformal geometry on your Lorentzian manifold and CR geometry on your, well, naive space. And so anything that is CR invariant downstairs should be conformally invariant upstairs. Now, if you impose the Einstein equations, then you break the conformal invariance. So you do not expect CR invariance downstairs. Instead, it will pick out a particular contact one form. So this is what, then you get pseudo-Hermitian invariance. So this is the key point. So there are people like, like myself playing parts on Rod Glover. So a few years ago, I told Rod well, the Einstein condition is not conformally invariant, I said, but no, it is conformally invariant. So the point of the tractor calculus is to turn some of these things that we see as not conformally invariant, like an Einstein metric, as being an additional structure on the conformal manifolds. And so perhaps this pseudo-Hermitian structure on the CR manifold that comes from the Einstein condition may be seen as an additional structure on the CR manifold. I'm not entirely sure. But in classically speaking, we cannot expect the Einstein condition to reduce purely to a CR invariant data. There has to be a choice of contact form. So, yeah.
Who else? No? Okay, thank you again. Thank you.